Okay, Assalamu alaikum everyone. Uh, Welcome to lecture 22 of data mining. Today, basically, we will complete our discussion on outlier analysis. We had started outlier analysis in the previous lecture. We discussed a number of techniques and ideas that are typically used for detecting outliers in data sets. In general, those techniques can be supervised and unsupervised as well as hybrid. And we discussed some examples of unsupervised techniques. We talked about statistical based techniques. We talked about proximity based techniques. And within the proximity based techniques, we talked about the distance based outlier. And we also talked about a density based approach called LOF, local outlier factor. We might continue, we will start with LOF again today, although we had completed it last time, but I'll quickly go over it again. After that, I'll talk about reconstruction-based techniques and then finally a bit about supervised techniques. So that is basically the agenda for today. Okay, is there any comment or question from your side? Okay, any questions uh, about what we had done in the last lecture or anything else? Okay, in the last lecture, we had talked about local outlier factor. This is a density-based approach for finding outliers in data sets. So I'm going to write the equations for this approach again, and we will quickly discuss how it works, and then we'll move on to reconstruction-based techniques. So local outlier factor. So this is basically a score that ranges between, in general, between 0 and greater than 0. So I should write it. So this is a score that is in general greater than 0. And of course, we will discuss this later on. You will get a better idea. So it's a positive score. And the greater the value, the more likely the object is going to be an outlier. So you generate this score for every object in the data set. And if the score is above a threshold, that object is considered an outlier. So K is an input parameter. K, as we mentioned before, is the number of neighbors that we need to consider for each object. So basically number of, okay? So this is an input parameter, and based on this, we define the neighborhood. So remember, we can define neighborhood using a fixed radius, or we can define a neighborhood using K. And using K to define the neighborhood is slightly better because it is not fixed and it adjusts to the density of the data set. So if a region is dense, then the neighborhood will become smaller because you will find the K objects in a smaller region if it is dense. If the neighborhood is sparse, then the K objects might be far away and you will get a bigger neighborhood. So it adjusts to the density of the data set. So there are a number of equations that we'll go through. So the first one is K, distance for any object A. Okay. So this is basically the distance to the kth nearest neighbor. So in other words, you can think of k distance as the radius, the you can say multidimensional radius of the neighborhood defined around A. Okay? And as I said before, this radius would adjust. In a dense region, this radius would be smaller, and in a sparse region, this radius would be larger. And then we have another a set N A. This is the set of objects in the neighborhood of A. Okay? And basically, as we mentioned last time, N A can be in general greater than or equal to K, because there might be more than one object that is at the same distance, the kth distance from the object. So in general, this can be greater than K. It can be equal to K, but it can also be greater than K. So after this, we define some local parameters for you can say distance as well as density. One is the reachability distance of an object A from an object B. So this is defined as a max of two terms. From two terms, the first term is actually the K distance of object B, not A. And then the second is the actual distance between A and B. So we take the max of these two. So the intuition here is that we are kind of, you can say, thresholding the distance. If object B is, if object A is within the neighborhood of object B, then we fix this distance to the K distance of B. Otherwise, it's just the actual distance if it is greater than that. Okay. And then after that, we basically define a density, which we call the local reachability density. Or you can also call this as an inverse average reachability distance, जो ऊपर हमने निकाला हुआ है. तो इसको हम इस तरह लिखेंगे 1 divided by, so we have a sum over all objects B in the set NA, okay? And this sum, of course, we are going to compute RDAB, and then we divide by the size of the neighborhood of A. ठीक है? So in other words, ये मैंने ऊपर 1 लिखा हुआ है, नीचे density लिखा हुआ है. If you rewrite this, n would become above, and then you have the summation below. So this is actually density. So that's why this is LRD is also called local reachability density. And as I said before, it's also inverse average reachability distance. Okay. So this number actually is a local density parameter. So it looks at the neighborhood of A and looks at the density reachability distance of those points. So if the neighbors of A are in dense region, then this value would be smaller. If the neighborhood of A is in sparse region, then this value will be larger. And then finally, based on this, we can define the LOF of A, which is actually the weighted average. So 1 divided by N A into, we have a sum for all B in N A, and then we have the LRD, local reachability density of B divided by LRD of A. Okay. So if LRD B of every point in the neighborhood of A is the same as LRD A, then of course this sum would be equal to N, and of course we are dividing with the neighbors of N, neighbors of A, which is also N. So this will give a value of 1. So LOF 1 means that object A and its neighbors lie in the same dense region, or their density is comparable. So LOF is equal to 1. This implies that A and its neighbors okay? And what we are interested in is, of course, LOF greater than 1. So when LOF is greater than 1, then the neighbors are in more dense region and LOF is in less dense region. So this would imply that X is likely, A is likely an outlier. And of course, we will have to threshold this to find specific outliers. Or you can, of course, rank your objects based on LOF and then let a user decide where to cut off and identify the outliers. So that's essentially it for LOF. So LOF is a density-based approach. It's better than your distance-based outlier. But of course, its computational complexity in general is going to be n square, because you have to look at each object and then you have to build a neighborhood for each object, which in general means that you will have to, once you pick an object, you have to look at all other objects. So that's where you get the n square. But if you have some nice way of indexing your data set based on spatial locality, you might reduce this somewhat. So I think you can reduce it maximally to, let's say, O n log n after using some spatial indexing technique. ठीक है? Okay, any questions so far? So LOF is relatively popular in practice. So it's generally considered to be a relatively robust technique and is applied fairly widely in practice. Uh, there aren't any major limitations for this technique. Uh, you need to define, you need to be able to define similarity between objects, distance between objects. So that could be defined in any way. It could be done for numeric data set as well as for categorical data sets. As long as you have a function that quantifies the dissimilarity between objects, this technique should work. So you don't need objects to be numeric for this technique to be applied. Although it works better for numeric data set, but it's not mandatory. There are actually many variations of LOF that have been proposed over the years, and some of them are tailored for, let's say, categorical data sets. But of course, we won't be discussing these techniques here. You might find them in the literature or in some implementations out there. Okay. So now let me move on to reconstruction based approaches. These approaches are relatively newer in the sense that although the idea is not, you can say, rocket science or wasn't known before, but these techniques gained popularity in practice recently. So the idea here is that whenever you find a lower dimensional representation of a data set uh, using any technique like SVD, for example, you tend to capture the main characteristics of that data set, the core behavior of that data set. So let me repeat that. So let's say your data set has 100 dimensions. You use, let's say, SVD to project it into 50 dimensions. So those 50 dimensions would retain the maximal strong information in the data set. The less strong or anomalous information would not be retained. That is by design of those dimensionality reduction techniques. Now, if you now reconstruct that original dimensions from those 50 dimensions, that information, the core information would be retained and the noisy stuff would be removed. And that noisy stuff, the assumption here is, the hypothesis here is that that is information that is outlier, that is anomalous information, that is not the core information in the data set. So we have now reconstructed it by removing some of the noise in the data set. And then basically we compare the reconstructed and the original point, and the difference between the two is a measure of whether a point is an outlier or not. So, okay, so this is the idea. Let me now make it a bit more concrete. So let's say, so as we had discussed before, we have n objects and each object is represented by m dimensions. Okay? And object, of course, is the vector x. And all objects of m dimension can be captured in a matrix X, capital X. So this matrix would be an n times m matrix. Okay? So m is the original number of dimensions. And the small x is actually a row in this matrix X. So that is one object in the data set. Okay? Uh, okay. So, so this technique, I will start with explaining using SVD, singular value decomposition, which is a dimensionality reduction technique. SVD, by the way, हमने cover किया था ना data preprocessing में. I've kind of forgotten. I think cover तो करता था मैं. I don't remember right now. I think I covered it a little bit, but let me just write the equations. So basically, SVD decomposes a matrix X, which is a data matrix, into three matrices. You have a matrix U multiplied with a matrix sigma or S, then multiplied with another matrix V transpose. Okay? So this is a decomposition of the original matrix. So SVD is actually a decomposition, but in this decomposition is done in a specific way, retaining the maximal variance information in both dimensions, in the dimensions M as well as in the dimension N. So the matrix U is capturing the maximum variance information in dimension N, which is the number of objects. So this matrix is basically N by N matrix. ठीक है? जो आपके पास V है, this is an M by M matrix. और जो आपका S है, जो S है, this is in general a N by M matrix. And this matrix S is a matrix of eigen values or singular values actually along the diagonal. So it's a diagonal matrix. ठीक है? Okay. So, but since we want to obtain we want to reduce the noise in the data set, we will drop some dimensions, and the U and V matrices have their vectors ordered, meaning that their columns are ordered. The first column retains the maximal information, maximal variance for that dimension. The second, the next maximal variance, and the third, the next maximal variance. So in other words, जो U है, this is based on the covariance of documents, meaning that how documents are related to each other, while V is based on the covariance of the columns, the features. Okay. So in either case, so we want to do a reduction in size. So let's say we choose some dimensions K, which is less than M. Okay. So then we will modify U. Let's say U prime हो जाएगा ये. This U prime would then become an N by K matrix, and my V prime would become a M by K matrix, and my S singular value, here I will only retain the first K rows and first K columns. So this would then become K by K matrix. And of course ये भी prime, ये भी prime है, ठीक है? So now if I do this, then I can get a reconstructed form of my X. So this would give me U prime multiplied by S prime multiplied by V prime transpose. So my X prime is now in the same dimensions. It will still have N by M. It's an M by M matrix, but now this is a reconstructed matrix. And this reconstruction is done after we have projected or embedded the data set into K dimensions and then reprojected it back into M dimensions. And the idea is that those K dimensions retain the core information in the data set, in this case, variance. And once we have projected it back to the full dimensions, only the core information is retained, the noisy information is discarded. Okay? So now let's talk about a specific object X. ठीक है? एक specific object X है और उसी specific object का फिर X prime भी होगा after we have projected it back into the full dimensions, ठीक है? Using SVD. So the difference, the norm between the two, you can think of this, if X and X prime are vectors, then you can actually compute this as X minus X prime. So X and X are vectors. I'm thinking of this as a vector. So ये फिर transpose हो जाएगा. This will give me a row vector. Then you multiply it with X minus X prime again. So in other words, dot product ले रहे हैं S minus X prime का. ठीक है? So this will give me a scalar value. So this scalar value is telling me how different this new point is, which is the reconstructed point X prime from the original point. Okay? So it turns out that since X prime में noisy information निकल गई है, anomalous information निकल गई है, तो if X is so if X is a regular, you can say, is a regular object, not an anomalous object, then this difference would be small. But if X is an outlier, then this norm would be larger. So in other words, we would then, let's say I call this a score. Score for X is basically then given by X minus X prime transpose X minus X prime. Okay? So this is my score. If this score is greater than some threshold, then X is an outlier. Okay. So any questions here? Because this idea is intuitive, but as I said, this has become popular in the last 10, 15 years. It was not used before for outlier detection, and it has given good results. Of course, I'm going to mention another technique after this that would make it even more powerful. So far we have used SVD, which is a linear transformation method. But as we'll see next, we can use a neural network as well, which would give us a non-linear transformation, and that can possibly handle more complex data types for outlier detection. But okay, first of all, ये idea समझ आया? So the threshold, of course, like in other outlier detection techniques, has to be decided by the domain expert through interactive sessions. Okay. Okay, so now let me move on to the more popular version that is used using the auto-encoder neural network. So the autoencoder neural network, it's a neural network that takes as input an object X, and the output also is the same object X. But along the way, it reduces the dimensions to a lower dimension. So it has actually two steps, an encoder and a decoder. So first of all, by the way, कुछ idea आपके पास neural networks का है? Because neural networks as such मैंने cover नहीं किया इस course में. Although the idea is very simple for neural network, but since we have not touched it, and for those who don't know any idea about neural networks, slightly वो confusing होगा. Anyone who has absolutely no idea what a neural network is and what it consists of?
No, sir.
So I guess, so at least all of you have some idea what a neural network is. So a neural network is basically an input-output mapping machine in general. So input to output mapping. And this mapping goes through a number of layers. Okay? And while it goes through a layers, it goes through transformations. And these transformations in general are non-linear. Okay? So usually that non-linearity is brought in by some activation function. Okay? So let me write the equations and then maybe I'll draw a slide diagram for it. So we have an activation A that's an output. This is given by some function G or some matrix W. This is the weight matrix multiplied by the input X that we are talking about plus another vector of parameters B. So B and W are parameters. B is a matrix, sorry, W is a matrix, B is a vector. And of course, X is a vector, it's a input point in M dimensions. Okay? So let's say, so X is M dimensional. Okay? So X is M dimensional, so this X is also an input. This is multiplied, or W multiplies with X to give you the output A. So A, we can reduce it. So let's say M आपके पास, so A could be K dimensional and K is less than M. Remember हमने ऊपर जो कहा था कि we would like to reduce the dimensions. ठीक है? So if these are the dimensions that the matrix W, sorry, which is a parameter matrix, इसका पर size क्या होगा? इसका size होगा K by M. And then the B, which is also a parameter, bias parameter typically कहते हैं neural networks में, this would be of size K. So ये parameters हैं. ठीक है? So, and the function G usually is a nonlinear function. So G typically can be tangent hyperbolic. So unlike SVD, SVD has a linear transformation. This is a nonlinear transformation. So अब A जो है, this an embedding of X. Just like in हमने X prime वहाँ निकाला था. So it's an embedding of X, or you can say that we have encoded X as A. So A would then of course be X prime. using notation that we used before. ठीक है? Sorry, x prime नहीं है ये, sorry. X prime तो बाद में आएगा. ठीक है. So now we have encoded it. Now we have to decode it back to the full dimensions. ठीक है? So we now get x prime, some function g of another parameter matrix, w prime इसको मैं कह देता हूँ, of a as input plus b prime. ठीक है? So अब यहाँ हमारे पास हमने आउटपुट भी उतनी डायमेंशंस लेनी है. So x prime is m dimensional. ठीक है? So x prime is m dimensional and a of course was k dimensional. So if that is the case, w prime का size क्या होगा? So w prime का size होगा m into k. और b का आपका b prime का इसका जो डायमेंशंस होंगी इसकी होंगी b prime की होंगी m because this is output layer. ठीक है? So now this is the reconstructed output, but now of course it goes through a nonlinear process. And these parameters, all these parameters W's and B's, we learn through a supervised approach. And supervised सुपरवाइज मैनर किस तरह है, जब आपने x इनपुट दिया था उसका आउटपुट भी x होना चाहिए. बट ऑफ कोर्स हम आउटपुट क्या कर रहे हैं, we are outputting x prime. So we are trying to minimize now the difference between x and x prime, and then based on that we are learning the parameter w and b, w, b and w prime and b prime. ठीक है? So once you have learned the network, then उसके बाद फिर you simply have to pass a new object x through the network and it will output x prime. And then if that x prime deviates significantly, or the norm जो है x minus x prime is large, then as before that is likely to be an outlier. So एक तो ट्रेनिंग प्रोसेस है. ट्रेनिंग प्रोसेस जो मैंने ऊपर सारा बताया, दैट्स पार्ट ऑफ द ट्रेनिंग प्रोसेस. आपके पास एग्जाम्पल्स थे, पूरा डेटा सेट था जिसमें ऑब्जेक्ट से जो एक्स मैट्रिक्स मैंने ऊपर बताया है उसमें इनपुट आउटपुट दोनों x ही हैं. ट्रू इनपुट इज x, ट्रू आउटपुट इज आल्सो x. But of course the network is outputting x prime. We are adapting the network such that we want to make sure the loss है x और x prime के दरमियान वो कम हो, को loss function minimize कर रहे हैं. And in that minimization we are fixing w, b and w prime and b prime. जब ये fix हो जाते हैं w, b और w prime और b prime, फिर you have a trained model. अब इस ट्रेंड मॉडल में जब भी आप कोई नया ऑब्जेक्ट x देंगे वो x प्राइम इसको आउटपुट कर देगा. अब आपने जैसे हमने पीछे किया था उसका जो स्कोर होगा, आउटलायर स्कोर, would be given in the same way, x minus x prime transpose x minus x prime. And if this is greater than some threshold, then this is likely to be an outlier. So we are basically then using an auto-encoder to reconstruct our data set by first projecting it into a lower dimension k. K is in general going to be less than m. And based on the hypothesis that if you project it to a lower dimension, you are retaining the core information of data set. The noisy information, the non core information in the data set is kind of removed. And then, of course, we reconstruct it back to the original, but that's a way of training this neural network. And the reconstructed and the original is then compared to tell us whether this is likely an outlier or not. So any questions?
सर जब हम x को एज इनपुट देंगे और फिर आउटपुट भी x ही कैसे हो सकता है? अगर उस पर कोई ऑपरेशंस परफॉर्म हो रहे हैं तो वैसे भी तो चेंज हो जाएगा.
Could you speak up a little bit?
सर मैं ये कह रही हूँ कि जब हम x इनपुट देंगे और फिर x ही आउटपुट कैसे होगा अगर उस पर ऑपरेशंस परफॉर्म हो रहे हैं और रिडक्शन हो रही है तो?
नहीं, x तो हमारे पास डेटा सेट है ना. लेट्स से x इज सम एग्जांपल इन योर डेटा सेट. सो लेट्स से मैं कोई इसकी 1.5 और 3, लेट्स से 3 डायमेंशनल इनपुट है. ठीक है, तो 3 डायमेंशनल इनपुट है और जो a है वो लेट्स से मैं 1 डायमेंशन कर देता हूँ, कोई भी वैल्यू आ जाती है 1 डायमेंशन 0.25. अब फिर वापस जो x प्राइम है ये वापस मेरी फुल 3 डायमेंशन पे आ रही है. तो अब इसमें जो आएगा मेरे पास, तो 1 लेट्स से 0.23, लेट्स से 2.5 कोई वैल्यूज आ जाएंगी. मेरे पास x प्राइम और x दोनों आउटपुट, मतलब x तुम्हारा ओरिजिनल डेटा सेट, x प्राइम जो है वो न्यूरल नेटवर्क ने आउटपुट किया. और ऑफ कोर्स न्यूरल नेटवर्क जब ट्रेन कर रहे हैं, वी आर ट्राइंग टू इंश्योर कि x शुड बी एज क्लोज टू और x प्राइम शुड बी एज क्लोज टू x. जब वो ट्रेन हो जाता है, ऑफ कोर्स 100% क्लोज तो नहीं होगा. द अजम्पशन इज कि जब आप कोर ऑब्जेक्ट देंगे, मेन ऑब्जेक्ट देंगे, वो क्लोज आएगा टू इट्स ओरिजिनल ऑब्जेक्ट, बट जो आउटलायर देंगे उसका डिस्टेंस ज्यादा होगा, इट विल बी फर्दर अवे. और वो हम क्वांटिफाई कर रहे हैं यूजिंग दैट L2 नॉर्म और द स्कोर जो मैंने ऊपर लिखा था.
ठीक है सर.
तो इसमें ऑब्वियसली थोड़ा सा वो न्यूरल नेटवर्क का एस्पेक्ट है. सो ट्रेनिंग इज डन फर्स्ट and that will, after training, and of course for training you need of course all the data set X. और इसमें ट्रेनिंग में जो इनपुट आउटपुट होते हैं सुपरवाइज्ड है ना, तो वो दोनों X ही हैं. ठीक है ना, जैसे जनरली न्यूरल नेटवर्क में एक X होता है, एक Y होता है. लेट्स से आप X इनपुट कर रहे हैं और आउटपुट आपका लेबल है, लेट्स से उसका क्लास लेबल है. But here the output is also X. We want to get X back. So that's why this is called an auto-encoder. We're trying to encode the examples itself. Okay? And in this training process, of course, we are learning the parameters, or fixing parameters during training. So once the parameters are fixed, we feed forward any new object X to get X prime. And then after we have gotten this, we compute the score as before, X minus X prime. Okay? And if the score is large, then it's an indicator that this is a outlier. So I would say that recently ये काफी टेक्निक इंडस्ट्री में यूज हो रही है. So that's why I covered it here. और ये एक्चुअली डेटा माइनिंग की जो बुक है हैन एंड कैम्बर की, उसमें ये नहीं है. जो दूसरी बुक है इंट्रोडक्शन टू डेटा माइनिंग, उसने ये डिस्कस किया हुआ है. But as I said, in practice or in the industry, this is quite common now. LOF के बाद, I would say LOF भी अब बाद में लोग देखते हैं, पहले ये try करते हैं auto encoder. But nowadays, as you know, neural networks are both popular as well as powerful. They do give good results. So लोग पहले इसी को ही try करते हैं and then look for other options. And of course, as you know, a neural network is very flexible. Input इसको categorical भी हो सकती है, numeric भी हो सकती है. And as you can see in the training process, कोई आपको similarity function define नहीं करना पड़ रहा previously. वो खुद ही learn करता है. There is no similarity function that you need to specify upfront. For example, in LOF, you need to have a similarity function. There is no need for a similarity function here. It learns the similarity function itself automatically. Embeddings ये खुद ही learn कर लेता है, encodings खुद ही learn कर लेता है. ठीक है? Okay, so let's see. So I think let me quickly go into the last topic then, if there is no question. So far we have actually looked at only unsupervised techniques. Of course, you might ask, auto-encoder में supervision हो रही है training के लिए, but that is unsupervised in the sense that we are not using any other external information. हमारे पास कोई information नहीं थी कि ये object outlier था या नहीं था. हमने x भी input दिया, वही x output दिया. फिर वो model train किया. So it's still unsupervised in that sense. ठीक है? So अब उस sense में I am talking about now a supervised approaches. So in supervised approaches, the assumption is you have a data set X, I, for which you have the label Ci. I is equal to 1 to n. So Ci is either 0 or 1. ठीक है? 1 means outlier. So in other words, कि आपके पास कोई ह्यूमन ने, किसी और प्रोसेस ने आपको कुछ डेटा लेबल करके दिया हुआ है, आपको बताया हुआ है कि ये आउटलायर है और ये आउटलायर नहीं है. ठीक है ना? इन ऑल द प्रीवियस एग्जांपल्स दैट वी हैड स्टडीड फॉर आउटलायर डिटेक्शन, उसमें ये इंफॉर्मेशन नहीं थी. So this is the supervision that we are talking about here. And that's why these techniques are called supervised techniques. So if you have such a data set already available, then इसमें standard classification techniques लग सकती हैं. So this is a standard classification problem where you learn a model that maps X to C. ठीक है? जैसे हमने ऊपर न्यूरल नेटवर्क बनाया था ना, वो मैपिंग कर रहा था X to X. Here we now build a neural network or some other classifier that maps X to C. अब इसमें भी जैसे ऊपर भी X X दोनों अवेलेबल थे, यहाँ हमारे पास ट्रेनिंग डेटा सेट में X और C दोनों अवेलेबल हैं, तो हम एक न्यूरल नेटवर्क बना सकते हैं. ठीक है? So once the neural network is trained, then you give the neural network a new X as input, and you will get C as output, which is the label for that object. And of course, this label can be made continuous as well. It could be a probability if you like. So it could be a probability between 0 and 1. So if it is 0.7, you can say that this object is, the probability for this object being an outlier is 0.7. Or it could be just two values, 0 and 1. If it is 1, then it means that this is an outlier. If it is 0, then it means that it's not an outlier. So you can use any classification can be used, so including neural networks. Okay? So any classification technique can be used to do this, to learn this, including neural networks. But there is one slight issue that you will have to consider while building classifiers. Um, Actually, it may not be a slight issue. It could be a bigger problem. So that issue is, so generally in data sets, the fraction of outliers is very small. ठीक है ना? And by definition, outliers are objects that do not follow the majority behavior in the data set. So that's the definition. So in the training data set that I mentioned above, उसमें फिर जो आपके पास examples होंगे for outliers, meaning that x zero वाले जो examples होंगी, there would be very few. ठीक है? So the vast majority of examples would be of regular objects or core objects, non-outliers. So classification algorithms run into problems when you have imbalanced class labels or imbalanced class distribution. Okay? So if you have a very few training examples for, let's say, outliers, and the vast majority are, let's say, not outliers. So let's say, for example, लेते हैं कि सिर्फ 3 objects थे out of 100 that were outliers. So for classification algorithms, it's very easy to label all objects as normal and still get an accuracy of 97%. ठीक है ना? If it labels all objects as outliers, if it all objects are not non-outliers, to 97% of the time it is correct, and only 3% of the time it's wrong. So it's still having a very high accuracy, but we are not able to solve our problem effectively. So this is the class imbalance problem in classification, और इसकी फिर कुछ techniques हैं जो की जाती हैं. Most of them are based on sampling. Many of them are based on sampling, so you will have to resort to that to solve this problem. ठीक है? So oversampling of the minority class हो सकती है या undersampling of the majority class हो सकती है. And then there are of course many variations. So एक technique जो commonly use होती है वो SMOT है. So I won't go into all details here. So this is actually an oversampling technique, symmetric multi something oversampling technique, SMOT. Okay, so that was one way of handling this. There are another class of problems which is called one class classification. So these are also classifiers, but they are focusing on only identifying one class. मतलब जो one class है उसके इर्द गिर्द boundary बना दी, और so that anything that comes outside that one class is then an outlier. तो ये one class techniques भी आप use कर सकते हैं. So I won't go into the details for this as well. So this is also a classifier which is, as I said, called a one class classifier. और इसमें most popular जो use होता है वो support vector machine. So which is also called a one class SVM. Support vector machine is a classifier. So one class SVM can be used to learn a problem for outlier detection. Okay, any questions? So any questions?
No, sir.
Okay. So actually, if you don't have any questions, so that is essentially what I wanted to cover for today. Uh, I think as I mentioned last time, so I would not be starting any new content next week. Uh, so next week, we can still meet during the regular lecture times, but for that, I would like to have your input, meaning that if you have any questions, then we can continue the session. And once you are finished with your questions, we'll then stop. Okay.
Okay, sir.
Okay. Uh, so, okay. So, a couple of announcements. You will have a quiz by the start of next week. Uh, and your exam most likely will be the start of the following week. And you will be given about 2 days to submit that. You will have a window of 2 days. And of course, once you have opened the quiz, you will have about 2-3 hours to finish it. And your project, of course, is due, assignment is due next week. The projects are due, I think, the week of May 17 and May 20. Okay, any questions, feedback, comments? Chale, but that's it. I think I hope you enjoyed the content that we covered in this course. Of course, the course kind of turned a quite different after the midterm because of change situations. And we were not able to cover more content. I had originally planned to cover also spatial temporal mining as well, but due to various situations, different situations, so I'm cutting it short. Okay then, so I think that's pretty much it from my side.